Okay, so I'm Brendan McDonald. I'm the CEO at Ekstera, and Ekstera is a startup, and we've developed and patented innovative new Stirling engine technology that allows us to convert heat sources into electricity. So, there we go. All right. So the problem we're solving here is that electricity demand is skyrocketing right now. Everybody's electrifying everything, and what we're seeing is grids can't keep up with demand right now. And they're looking specifically for clean, reliable, and affordable sources. So a lot of the renewables we turn to now struggle in the reliability aspect. And so what a lot of grids are doing is turning to fossil fuels like natural gas. At the same time, there's an incredible opportunity. When you look at energy production globally, 70%, 70% of the energy we produce globally is lost as waste heat. 70%. If we can convert even a tiny slice of this into electricity, that's a massive amount of energy. At the same time, this aligns very well with carbon reduction initiatives, because when you look at the pie chart here, in the difficult to eliminate emissions section, we have industries like steel, cement, load following electricity, all of which have enormous amounts of waste heat. So this aligns really well with converting their waste heat they already have into electricity, saving them money and reducing carbon emissions at the same time. The question, though, is what technology do they use to do this, right? So if you look around now, heat to power traditionally would be done with steam turbines. Steam turbines need to be massive to be efficient. So the steel mills that we've spoken to have said, we looked into steam, they cost a ton of money, they need to be huge, we don't have the space, we don't have the money. ORCs, organic Rankine cycles, is another technology that can convert heat to power. Same basic idea. They need to be really big to work well, and they need to be really big to make financial sense. So there's a whole bunch of applications where there's heat available, but they don't have the space and the money to use these massive 10 to 25 megawatt systems. So enter the Stirling engine. And if you might be familiar with Stirling engines, they're a 200-year-old technology. And so I'm a professor in mechanical engineering. And when we teach thermodynamics, you always teach Stirling cycles first. And you say, hey, listen, they're the best way to convert heat into power. They have the highest efficiency, and they're external, so they can use any heat source. But then the reality is, you look around, and there are no Stirling engines anywhere. It doesn't make sense. We have all this waste heat. Here's the best technology for converting that heat into electricity, yet there aren't any. So we started on this project by looking into why their max efficiencies are so low, why they're using only fossil fuel sources. And basically we discovered that past engines will follow this solid line right here. And this is a pressure volume curve. It's showing the amount of work produced. So if you're using traditional Stirling engine technology, all the blue area here is the work that's lost. And this was a fundamental drawback to Stirling engine technology. We would actually argue that past Stirling engines should not be called Stirling engines because they're not following the Stirling cycle. And when you add all this up, they're losing 30% of efficiency right off the top. And so our first challenge was, can we make a Stirling engine that properly follows the Stirling cycle, which is the dashed line here. So here's the data from our engine. And you can see, comparing the shape, we're able to much more closely follow the Stirling cycle. And that's why our Stirling engines are fundamentally different, and why we can start to tap into these heat sources that nobody could previously utilize. So how do we do that? That's the big question. What we've done is created a cam groove profile here. With advanced modern machining, we can create a profile that controls the motion of our displacer. So by following this groove, we're controlling the motion of the displacer and following the proper Stirling cycle. The second piece, I should forward this. The second piece here is our regenerator design. Regenerators are key to Stirling engine technology. What the regenerator does is it stores the heat as the air moves between the hot side and the cold side. And because it stores all that energy, means you don't have to add it in every cycle continuously. And in the past, they would just take things like steel wool and stuff it in there, and think that would be a great heat transfer medium, which is fine. But what we can do nowadays is use 3D printed metallic structures. And because we can 3D print the metals now, we can control the surface area precisely, and we can control the direction the air moves in. So we can make clever pathways to enhance the heat transfer. So those are our two patents. The regenerators is patent pending. The patents are already granted on the motion control system. So that's what allows our Stirling engines to achieve much higher efficiencies. This is our benchtop prototype here. So what we've essentially done now is we've made a unit, we've showed that it works, we have the data to support that we're following the Stirling cycle more closely, showing that we can do this very efficiently, and now we're looking at moving into the piloting phase or the field testing phase. And essentially what we want to do with our pilots is we install the Stirling engine right where the heat's produced. So our first partner is a steel mill, and we can literally mount the engines right on the side of the stack and produce electricity. The reason they love this is because it's hard to move heat around, but it's really easy to move electricity around. So if we can make electricity right where the heat is, they love that. And essentially, it's easy to install, but what the steel mills really want is no interruption to their process. So we can go down, they don't care. When they're in a shutdown, they set it up so we can install it, and literally nothing can disturb their system. This is our first partner here. This is Gerdau Steel, and this is us at their Cambridge facility. They're the largest producer of long steel in the Americas. And what we've done with them is they've actually agreed to fund our first pilot. So we're doing a small scale pilot this fall. That's just 1 to 5 kilowatts, very small unit. Once they're satisfied that that unit is reliable, immediately they want us to install a larger scale one next year, so 2026, to align with their shutdown schedule. We're looking for fall of 2026 to do a full scale production unit. So that's where we are right now. We're also looking at other partners. So this is the size of the unit right here. It's a CAD model because we're building it right now. And this is what it looks like. That's their stack right here. And we're going to install literally right on the side of the stack. As I mentioned, that's a small 1 to 5 kilowatt unit. What's kind of mind-blowing here is they gave us the exhaust data for that stack. That stack is at 800 degrees Celsius, and there's 5 megawatts of thermal energy. 5 megawatts of thermal energy in that one single stack from one single furnace at our steel mill partner. So if we take even a fraction of that energy, that's a huge amount of energy. If we could come in at 20% efficiency, that's a full megawatt. We've also talked to cement facilities. There's a lot of waste heat off their kilns. So this is Lafarge. We toured the Lafarge plant, and they're very keen to work with us as well. They're in the range of about 450 to 500 degrees Celsius. Right now, with our engine development, we could do anything above about 300 degrees Celsius. And that's a delta T, remember? So normally the cold side is room temperature. So anything 300 degrees Celsius above room temperature, we could handle right now. As we get more efficient, we drive those temperatures down, but we don't think we're ever going to go past about 200 degrees Celsius for our heat sources. Another big one for us is oil and gas. So there's a lot of compressor stations. Same idea. Off these compressor engines, which are natural gas fired, they're about 450 to 500 degrees Celsius as well. Biomass is a big one too. So this is actually a local wastewater treatment facility with enormous amounts of biomass. Our engines don't care what the heat source is. So we can use biomass. We can essentially burn anything and put our engine on top of it and harness that heat. So this is why we're at Hannover Messe, because we want to learn about our customers' needs and understand who has waste heat available. So essentially, we're looking for more pilot projects right now with different kinds of partners. And we want to align the need, the quality of the waste heat with the need. And so essentially, in looking at what kind of waste heat people have, the electricity situation, because the economic viability of our engine relies on how much people pay for electricity. And also looking at the situation with their emission reductions. Because our energy is clean, we can reduce carbon emissions as well. So we're actually profitable in our situation with the steel mill. The payback period there is 15 months with our technology. That's projected at current rates. And so even without carbon emission credits, we're still profitable. But it's a really good nice to have. And sometimes if electricity prices are low, it can help the economic viability of our engines. So we are in Hall 2 in the Canadian Pavilion in the startup section. So come check us out. Happy to talk to you. We have a little model, a 3D printed model of our engine. So yeah, happy to talk about that. And that's everything for me. So thanks for coming. Appreciate it.